Today's topic deals with simple chemical nomenclature, or naming simple compounds. We have three classes that we want to focus on learning how to name, and that's going to depend on the type of compound we're looking at. The first type is ionic compounds, and how we're going to know ionic compounds is we're going to look for the beginning of the formula to have a metal or a polyatomic cation. This would be something like NH4, ammonia for example. There are several others, but ammonium is going to be the only one that you see in high frequency. Second classification will be molecular compounds. These will only contain non-metals in their formulas, but you have to be careful. Sometimes you can have ammonium in a compound with something like chloride that will be all non-metals but will still be ionic. So you have to kind of use your judgment on that. And finally, acids. They'll always have a hydrogen ion where the cation would normally be. So an H will take the place of a metal. Most of them exist in aqueous solution, but not all of them. Some of the organic acids will not be that way, but they'll also have really complicated IUPAC names. So we tend to just go with their normal acid name, something like carbonic acid or oxalic acid. Even though it would have a different IUPAC name, we tend to go with that. So how are we going to do this with ionic nomenclature? Well, we'll focus first on cations, or positive ions. They will mostly be comprised of the representative metals. That's groups 1A through 3A, which means we will lose 1, 2, or 3 electrons and form +1, +2, or +3 ions. And they will maintain their name as they show on the periodic table. For example, if sodium loses its 1 electron to become Na positive, that is going to have the name sodium ion. It's not going to have any shifts in its name. We can also have transition metals form cations. These are your D and F block atoms, and they will have multiple charges, and those will have to be indicated in their names with parentheses and Roman numerals. Examples would be chromium. Chromium comes in 3 flavors: chromium 2, chromium 3, and chromium 6 are somewhat common. The lower charges tend to be more common, but chromium 6 or hexavalent chromium is also found in nature. Zinc and cadmium, even though they're in the D block, are exceptions to this rule. They will always be positive too. They end out the D block, so they do not lose those electrons. They only lose their outer 4s electrons. Even though mercury is also in this location in the periodic table, it does not follow that rule because of special properties that are given to it by it being a liquid. It's able to share electrons between mercury atoms, so it tends to not follow that rule of always having a positive 2 charge. Silver is another one that's going to violate. Yes, it's in that group of transition metals that should have multiple charges, but it's almost always +1, and typically silver compounds are named without the 1 in parentheses. You can put them if you want, but it's not absolutely necessary. Last but not least are lead and tin. They are not in the D or F block. They are group 4 representative metals, but they tend to have multiple charges. They can be found in nature quite readily as +2 or +4. Even though the +2 is more common, you do need to know how to deal with the +4, and they will be named just like transition metals. Polyatomic ions, on the other hand, will just keep the name that they've been given. They've all been designated a name, and that's the name they'll keep. Anions are a little bit simpler. Our representative elements that form anions are groups 6A through 8A. We keep their suffix, so chlorine, for example, the suffix or the prefix is chlor. That's the root. And we add ide as their suffix. So chlorine, instead of the ine, we say ide. We add that as a suffix, so we become chloride. Polyatomic ions, again, keep the name they've been given, which makes things nice and simple. So here are some examples of how to deal with ionic compounds. Give the names of the following compounds. So we have Li2S. That's composed of lithium and sulfur in their ionic forms. Lithium, if you remember back, is a metal, so its name will not change, so it's going to be lithium. It's in group 1A, so that's representative, does not need a charge in its name, so it just remains lithium. And S is sulfur, but the root sulfur is going to produce sulfide as an anion. So Li2S will be lithium sulfide. Using similar logic, we can look at LiClO3 and know that lithium is going to be lithium. ClO3 is a polyatomic from the list of things that you're supposed to know, so that is chlorate, so that would be lithium chlorate. Chromium appears in CrCl6. Chromium is a D-block metal. So if we're looking at the D-block metals, we've got to try and determine their charge. So as we look at that, we see that chromium is bound to 6 chloride atoms, and each chloride atom happens to have a charge of -1 due to its location on the periodic table. So that means that chromium has given up enough electrons to produce 6 Cl negatives. That's a -6 charge. All compounds must be neutral, so chromium is +6. So when we name this, we're going to say chromium 6 chloride. Thinking in similar terms, hydroxides are -1, since lead is an exception and must follow transition metal rules. If we're looking at this, we have 2 OH minuses, so lead must be +2, so we would have lead in parentheses 2 hydroxide. Next, we have writing formulas for compounds. So this is going to be very similar. Aluminum oxide, we know aluminum's in group 3, so it remains Al. It's in group 3, so it's +3. Oxide is O. O is -2, so this becomes Al2O3 to be a neutral formula unit. With sodium sulfite, we've got sodium and we've got sulfite. Sodium is Na. It is positive. Sulfite is SO3. It is -2. So when I put those together, I get Na2SO3. Nickel 3 iodide. Well, the 3 is just telling me what nickel's charge is. So nickel +3, I -1, and I get NiI3. And then 10,4-phosphate. 10 is Sn. It is +4 according to this. Phosphate is PO4, -3. So I get 3 10 atoms and 4 of the phosphate unit inclusive. Next, we have covalent nomenclature, which is far simpler to deal with. Simple covalent nomenclature uses prefixes so that we can show how many of each atom is present. These are the Greek prefixes: 1 for mono, 2 for di, 3 for tri, 4 for tetra, 5 for penta, 6 for hexa, 7 for hepta, 8 for octa, 9 for nona, 10 for deca. We always put the least electronegative atom first, followed by the more electronegative atom. If you don't remember electronegativity, look it up in your textbook, but essentially the atom that behaves more like a metal, which tends to be the one closer to the metals on the periodic table. Prefix mono can be omitted on a first element, so if I have CO2, we don't call that monocarbon dioxide, we just call it carbon dioxide. And then finally, odd vowel combinations can be omitted. This tends to happen with things like hexaoxide. That doesn't roll off the English tongue very well, so we tend to refer to that as hex oxide. So here are some examples of how to deal with covalent molecules. Give the names of the following compounds. If I have 2 sulfurs, the prefix for 2 is di. We keep the name sulfur. 2 again, dichloride. If we're looking at N2S5, that is, or sorry, we're going to skip to NO2. Some of these you can do on your own. N2S5 is dinitrogen pentasulfide. NO2 would be nitrogen. No need for mono. And I've got 2 oxides, so I'm going to call that dioxide. N2O5 is dinitrogen, and then we would have pentaoxide, but we said that doesn't flow well, so we're going to shorten that to pentoxide. So I'll write that one out. Dinitrogen pentoxide. Notice the omission of the A. we want to write formulas for these guys, we just translate those prefixes back into numbers and use them as subscripts. So trisulfur becomes S3, and dioxide becomes O2. Diselenium, that's Se2. Monochloride is Cl. Tetraphosphorus, that's P4. Pentoxide is O10. O5, sorry. O5. Okay, with acid nomenclature, we have three types that we can do, and they're all based on the anion suffix. So we'll start with the simplest of these, which is anions ending in "ide." This is almost all binary compounds, like HCl, H2S, H3P, anything that's only two atoms. Also includes cyanide, so HCN would fall under this umbrella. The acid name will retain the root name of the anion. So if it's HCl, it's going to have chlor in it, and everything's going to be built around chlor. We're going to add the prefix hydro and the suffix ic to that root. So again, if it's chlor, hydro, chlor, ic. Those are the pieces. And then we add the word acid as an ending name. So hydrochloric acid. And that would fit the pattern right there. The next one are our anions that end in "ite, like SO3, -2, NO2, -1, just some of our sulfites, nitrites, phosphites, things of this nature. We're still going to retain the root, so if it's nitrite, for example, the NITR then is going to stay. We're going to add the suffix OUS, so nitrite, we take off the "ite and add "us", so it becomes nitrous. And we add the word acid as a last name. So NO2, HNO2 would be nitrous acid. There's our scheme for that. Last, we've got our eights. This is by far most of our polyatomics. So sulfate, phosphate, chlorate, bromate, on down the line. We still retain the root. So if it's bromate, for example, we're still going to use brome. This time we're just going to add ic, not hydroic, just ic. So bromic. And we still add the word acid, so HBrO3, bromic acid, and that's our pattern. Some interesting things we need to keep in mind. Sulfur, we don't use sulf as the root for sulfur. We use the word sulfur as the root. So we will not have sulfus or sulfic acid. They will be sulfuric or sulfurous. Phosphorus is the same way. We don't have phosphus or phospic. We keep it all the way out to the OR, so it will be phosphorus or phosphoric or hydrophosphoric acid. Here are some quick examples of acid naming. If I look at this, HBr is binary, so I know it's going to be hydro something ic. It's hydro. The root for bromine is brome, ic, acid. We're looking at H2C2O4. We have chromate back there, so 8 matches with ic. So that becomes chromic acid. We're looking at HCN. CN is cyanide. Ide goes with hydroic. So that is hydro. The root for cyanide is cyan. Add the ic, acid. And then HNO2 we did as an example earlier. Nitrite becomes ite goes to us. So that's nitrous acid. If we want to translate the other way quickly, we have oxalic acid. Acid tells me there are H's. Oxalate is C2O4, -2, so that means I need 2 hydrogens to go with it. Sulfurous is coming from sulfite, which is SO3, -2. I just need to complete that with hydrogens, H2SO3. And then hydrophosphoric, hydroic tells me it's binary, so this is P. P is -3, so I need 3 hydrogens with it. And that, in a nutshell, is simple chemical nomenclature.